coming, first of all of you, and Jose for inviting me to give and to share some part of my knowledge and research activity. Since I really do not know exactly which is your background in data analysis and chemometrics, you can interrupt me at any moment, because the important thing is that what I'm going to present will be enough clear to you. And so don't worry. I mean, you can interrupt in any moment. It's really not a problem. And don't think that any question you have in mind is stupid, because in my life I have never met a stupid question. I mean, all questions usually are really important for some reason. So I would really love this interaction. Also because I sort of didn't manage to prepare real exercise. So the idea is I will present some methodology, different methodology, but if looking at the slide you have in mind that you may have data sets that are similar or are different, and you want to ask what should I do in this case. So I really hope we can have this type of nice interaction today. So as you see, I put this image in the presentation because I really think that data fusion is not one method, and probably is not even a specific field. Is a bunch of different methods that we have developed during the year for several reasons, and that we use to get the better or the best integration among data which are different in nature. And when we want to do this, of course, we want to do this in a way that what we get will be enhanced. So the first part of my presentation will be about history of this word data fusion and what we want to do when we speak about data fusion. First of all, but this is something that is very clear to you, why we started of thinking of data fusion. Just because nowadays we got many data, and we get this data because our instrumentation is becoming fancier, which means on one hand some instrumentation is becoming faster, some instrumentation is becoming available and was not before. Many instrumentation is also coupled or hyphenated, if you prefer. And so the idea is that each instrument we use can get some aspect of the system we are studying. So an analogy can be with our senses. We have some senses, and when we appreciate a food, a landscape, or a friend, we usually merge in our mind all the information that comes from our senses. So basically, this is what we want to do with the data too. We want to study foods, we want to study tissue or a patient, we want to study the weather. Nowadays this is a real important question. We want to study environment, we want to study maths or whatever. So in this case, our approach is that probably we do not know a priori which is the best instrumentation to really understand and cope with our system. So one idea of using many is that we do not know a priori which is the best one. In other cases, we use instrumentation that are maybe cheap and portable, and in this case, maybe we have available many. So the idea is we use many because we have many, doesn't cost us too much. In other case, like in process, we have all the sensor that comes with the machinery control, and these sensors are always there. So we don't spend or invest extra money for this sensor because they already are there, because they serve one main purpose, which is to have our machinery under control or controlled. But nonetheless, this sensor does not register anytime the same value, and this fluctuation can be related to what we are producing, the intermediate product, the final one, and so on. Moreover, in medical diagnosis nowadays, we can analyze different body fluid. We can use different kind of in vivo spectroscopy. It depends on how wealthy is the hospital where we go, but we have several instruments. And a few things nowadays we also have, or we start to do. I will not speak about this specifically, but also we can merge textual information with spectral information. So I have not planned to speak about this, but in the end, if you are curious, we just did a first example, and I can transfer something from my computer. It was a thesis of a PhD. So basically, there is really many reasons why nowadays we get a lot of data. And also, I mean, having a lot of data is not the only motivation. The other things is that we change in the last 20 years, at least, our attitude towards, let's say, how to solve scientific question or how to solve practical life question. So we, in a certain way, abandon a bit the idea that we can have enough a priori knowledge to set up experiment based on our a priori knowledge. Now we are more on the side of what is usually called data-driven discovery. So we want the data to inform us a bit, and then we want to merge the information that comes from the data, analyzed as such, with our prior knowledge, and from this integration we go for a second step of experimentation that is more well-oriented. So of these two things that are fundamental, the reason why we need this methodology. If you look in the literature, the first times data fusion was used, and this is not strange because it happened with several methodologies, was in the military context, because they wanted to somehow to merge the information that comes from different sensors, maybe used to monitor what is happening in the field in the case of war or something similar. So one of the first definitions was a bit before 98, but was generalized in those years, is that data fusion is a formal framework in which are expressed the means and tools for the alliance of data originating from different sources. It aims at obtaining information of greater quality. The exact definition of greater quality will depend upon the application. So here there is already the idea that if data fusion is needed and is going to be successful, is because when we merge or integrate data together, what we can get out is more, is enhanced, is better than if we analyze the single data distinctly. So there should be a benefit, otherwise the play is not worth. Later on, Dana Lahat wrote a very nice review in 2015 about data fusion, and this is more mathematical or theoretical oriented, but it is more close to what we do in chemometrics. So it's more close to the idea of latent variable or principal component and so on. And so it's how to exploit diversity, which is the property that allows to enhance the use, benefit and insight in a way that cannot be achieved with a single modality. So I like this because the idea is that if you have a different view, and this different view in our case means different instruments that are based upon different physical and chemical principles, so this diversity is a richness, because maybe some of the information is replicated, but some is not replicated, and so a synergy can be established to enhance and to have something better. So this is probably what is more close to us. Data fusion is the analysis of several data sets, such that different data sets can interact and inform each other. The idea of inform each other, translated in instrumental data, is that maybe I can have more, if you think for example of chromatography, I may have overlap in retention times, and maybe with some instrumentation this overlap is stronger, so my chromatogram is more confused, less easy to resolve, and maybe I can have another instrumentation, maybe spectroscopy, which is completely different from chromatography, but maybe in this case what is overlapped in my retention times, in my chromatogram, is maybe very well distinct, because I don't know, maybe in the UVVs or in the infrared region or in the Raman, these compounds give different peaks. So inform each other means that since I have something in which my compound are resolved, I can sort of get this information, because when I look to all my sample, and all my sample are in common, the variation along the sample inform, especially if I use method like principal component analysis or partially squared. So if I use method that calculate component, so this method look at the variance through the sample, and if I have columns, so if I have a part of a spectrum which is more resolved, this will help also to resolve the other one. So the idea is that I can benefit because I can have this integration. Okay, that was, here you have some references, so for the one of you that in the future are interested more in this historical perspective, you can have this very nice review by Dana Lahat. Okay, so coming to us, why using data fusion? If you look to what is more, in a broad sense, the machine learning community, in this case, the main aim for them is to improve decision making. So the idea is that especially for robotic application, remote sensing, in this case usually I care less about the interpretation of my data. What I care about is to have sensors that help me to take decision fast and in a safe way. Imagine you have a car without a driver. What you want? You want a set of sensors that are able integrating information, and this can be vision, can be acoustic sensor, can be some other things that are able to tell the car where should go. So in this application, you really don't care that much if it is the vision sensor, which is, I don't know, in the front of the car, or if it is the acoustic sensor, which is on the side that has been the fundamental information. What you care is that the decision to the automatic pilot of the car is the right one. And the same thing is in other field. If you are controlling something, maybe what you really want is only a quick decision. And in the military application in the beginning, this was the main motivation, to have sensor that helps military to take a decision. Is this a risky situation? I have a terrorist there or not? Is this a suspicion movement or not? There may be a gun hide in some place. So I want sensor to help me to take quick decision. So this is one type of motivation. Another thing is that I want to improve the management of the knowledge of the system. In this case, usually we fuse very heterogeneous information, like textual, numerical, relation, and data that are flowing. So these are a lot of application in the web. When you want, for instance, to analyze the data that are around from different apps, different social media, and you want to combine this data, to fuse this data to have an idea of the habit of some customer or other things. This is also some one motivation. Another field that is developing, in which you have different sensors, is this field of very small sensors that can be wearable, that can monitor several functions of the body, if you think of an athlete or if you think of a medical. But there are also more, let's say, amusing application of this. And then also, potentially, if we will become very good to match textual data and instrumental data, we may, for instance, use all the things that we write, potentially in literature, in scientific literature, or imagining in a hospital, the tons of diagnoses that you have written. Maybe we can merge this information with clinical tests or with something else. So this is also another motivation. And usually, as a econometrician, and probably knowing your background, you are also in this motivation. So in this case, we want to enhance understanding and also capability of solving real problems by obtaining improved model. So in this case, we want to merge different data sets, because in the end, we want a model that is more smart, is more performing, will predict well, or will help us to better understand what is going on. In this case, we most of the time care about interpretation. So we want also to know which is the instrumentation that is most suitable. Do I have a specific information that comes from the Raman spectrometer instead of the infrared spectrometer, or from this liquid chromatography with respect to gas chromatography or something else. So we care at variance with the first. In this case, we care a lot also about interpreting the role of each single data set in the data fusion process. So in this case, we are also interested in assessing the commonality and the differences between the different data sets. And also, we are interested in interpreting which are the relation, the linkage between the different blocks. Why I spend some time on this contest presentation? Because of course, each one of us has his own problem, and this is our main interest. But we have to understand that other people has other problem and other interest, so there is not in principle a data fusion method which is good and one which is wrong, or one which is absolutely best, but any of them has been developed with one of these specific objectives in mind. So it is important that we know that people have different objectives, because maybe when we select a method, we can also ask ourselves, in which context has been developed? Is this context close to mine, or can I borrow something interesting from this field or not? So it's also a way of taking a decision. I use this method instead of this other one. Also to see in which context has been developed and has been functioning. So, another thing that is important to know is a bit of the names and vocabulary, because in different articles people may use different names as usual. You are not surprised by this, because I mean you live in a country with and you manage several languages at the same time. So we tend to replicate this diversity in languages also in all our methods for some reason. So the data sets may be designed by different terms. One can call simply data set or data block. Then you can call them multi-set analysis. For instance, there is one methodology in chemometrics which is very well developed, which is called multivariate curve resolution. And in this case, you speak about multi-set, and what you have in mind is also fusing different set of data. In chemometrics, quite early, analyzing different data set all together, what's called a multi-block analysis. In more close to machine learning, this review by Lahat that I was referencing before, the term used is multimodal, because each data set has been acquired with a different modality, so they use the term multimodal. And then you can speak of data fusion, but in many papers you use this terminology, linked data or coupled data. So when you put together different data sets, someone said that you link them or you couple them, and this is also some other things. And so in perspective, what define the starting data for data fusion is a collection of data block with a connection between the block consisting of shared mode.
What is a mode in this context? Shared modes. What does mode mean in this context?
Okay, mode in this context means the dimension of your data set. So we are usually happy to have two-dimensional data, where we usually we do like this. We put the sample in this direction, we put variable of spectra in this direction. So in this context, we say that this is one mode, mode 1, and this is mode 2, a second mode. So the idea is that if I want to merge data, so I want to fuse data, there is one basic condition that should be fulfilled. One mode should be in common. Or, yes?
No, I wanted to add that the naming in planetary science is called combined science. It's data fusion as well. Yes. It's just, I mean, you will find in the literature the important things that you understand what they actually talk about.
So you should have one mode in common. So for instance, the same number of samples. Or you should have a method that can reconduct you to this situation.
Should they be the same number of samples or the same samples? Like, can it be either or both?
Usually both.
Usually both.
At least a part of them. Because if I change, I mean, this is a good question, because I may think, okay, I measure pairs. So as far as I have pairs here, and I have the same number of pairs, this means that I have the same sample. But in the data fusion context, this means that if I do, I don't know, CCMS on the volatile fraction in the ether space of the pair, and I do near infrared, somehow should be the same pairs. So I should sample the same. Why this? Because if I want to link this data, should be the same sample. Because imagine that I analyze my urine and the urine of her. Come on, we are two different individuals, okay? We are two women, and we are two women of the same, I don't know, of the same origin as race, but then we are very different. So there is no reason why I should think that I can match my clinical test with her clinical test. So in this case, the answer is both. There should be some shared information that really refer to the same sample. Of course, sometimes can really be the same sample, because if I have a non-destructive analysis, I can exactly measure spectroscopy with different spectrometer on exactly the same sample if I use non-destructive. In other situation, if my technique is destructive, is a subsampling from the same bulk sample. And of course here I should be careful, because I should have a representative sampling in both cases. And this is not at all obvious. So if I have to teach something to you today, this is the very first lesson. Think really a lot about the planning of your experiment if you want to do data fusion, because you have to collect data that are meaningful. So this sampling, for instance, is a very relevant issue when you use one technique which is destructive and maybe one which is not destructive. Because, I don't know, if you take an hyperspectral camera, you can have the whole pair acquired, and you can have information from the whole fluid. Then imagine you have to use something which you need, I don't know, high resolution mass spectrometry, you need a very, very small sample. So how this come to be representative? Because otherwise you think that you are merging data from the same sample, but actually, maybe in one data set you have a huge heterogeneity or more heterogeneity, and the other is very homogeneous, and you may get wrongly the idea that they have no information in common, just because you are looking different spots, or in one case you are looking the whole, and in the other a single very small spot. So that's, I think, was a nice question and an important one, because there are methodologies that may allow you maybe not to have the entire sample altogether, but at least a part of it. At least a part should be the same if you use instrument 1 and instrument 2. At least some should be both. Same type and exactly same sample. And this is a very easy trap, especially when your techniques are very different. Because maybe you do not think of this problematic of representativeness, and maybe with one technique you have, I don't know, 10 preparative steps. So you think it's the same sample because you start from aliquot from the same sample. But then if your preparation process is very long, you should ask yourself if this is a representative and if this remain the same sample, or during the preparation you do separation. So some part of your sample is filtered, you purify it, you may do many operations that change the nature of your sample. Then you are not anymore confronting the same things.
Marina, sorry, I have a question. What about, it has been clear so far that the sample has to be representative. But what about if the two techniques that I'm choosing, or two or many techniques I'm choosing, they don't give relevant information? In the sense, let's imagine I want to analyze, I don't know, a sample of a drug, a pharmaceutical drug, and I want to analyze the organic part. Because of my ignorance, or I don't know what, I'm analyzing this by GCMS and ICP, for example, a technique that doesn't give just noise. Are these approaches able to provide me information that I'm not choosing the right technique, or is it a fundamental condition, this very careful planning of the experiments?
In this respect, not, because in this case, as far as you use the same tablet of drugs, and so you use elemental analysis, and you may have trace or ultra trace because it's very pure, so you will have a very boring information from ACP-MS. But in this case it's okay, because if your shared mode is the sample, this is coherent. Then you have completely different information. But that is fine, because we can see that we have methodology in which we can assess which is the contribution of the spectroscopy or the chromatography, and which is the contribution of the elemental analysis. And in this case, you may see that the contribution of elemental analysis is very, very little, and you may even discover that for some specific sample, contrary to what we assume, there are some elements that are more present, and this can be an indication of contamination, for instance. So this is okay, because it's the shared mode that should be the same one. If you are in the opposite situation, so for instance the shared mode for you is the same instrumental technique, so You have chromatography on different sample, and in this case, you have acquired the same in the same condition, and you have the same setup. So in this case, you say, okay, I'm sure that I have used the same column, the same method, etc. So, and I have acquired different sample, but what is in common is the chromatographic range. So in this case, the shared mode will be the variable. So in this case, the methodology and the instrumentation should exactly be the same. And in this case, I want to see which are the differences of the sample with respect to this same variable. So it's the shared mode that they should match. Other question? Okay. So, which is the important aspect? Understand the nature and the structure of your data, and this is the most important one, clearly state the inherent research question that are posed. This is something that probably any time a chemometrician give a course to you will repeat, that if you do not know what you want, you will never get an answer. In another, we can see this in another way. If you know Alice in the Wonderland, there is a point in which the rabbit asks Alice, in which Alice asks the rabbit, which way should I take? And he say, where you want to go? And she answers, I don't know. And the answer of the rabbit is, then any way is the same. And it is a bit with that analysis. If you don't state clearly your research, it's very difficult to decide which way you should go, either with instrumentation or data analysis. So probably we will repeat this many, many times in every seminar, but I think it's worth to do. Okay, so now the question is, can we mix apple and pear? So can we mix things that are very different? And the answer is yes. And in data fusion, we have this very, very general framework that we define three main approaches that we call low-level data fusion, mid-level data fusion, and high-level data fusion. And I try to explain to you what these terms means, what this approach do with this example of apple and pear with fruit. So for instance, if we do a fruit salad, in this case,